Today we're going to talk about the differential transformer paper. This paper proposes a new architecture for a certain problem in the transformer. So the transformer architecture, which powers ChatGPT, for example, the main problem with that, or one of the problems, is that it tends to over-allocate attention. So it gives high attention scores to information that is not relevant based on what it's looking for. So think of it as a finding a needle in a haystack. So the problem is that it assigns a decent attention score to the needle, but the hay in the haystack, it also has a attention score that is close enough. And the problem is that the attention score of the needle, it sort of gets drowned out by all of the attention scores here. Like that difference, like what we really want is the difference between the needle and the attention score of the needle and the attention score of the haystack to be very large. And they show this in this example here. So let's look at this example. You have a lot of context here. Okay, the context is comprised of many documents. So let's just say each one of these bars is a document, including the answer. Most of the context here is not relevant based on what we're looking for. So the query is a vector that contains something it's looking for. What it's looking for is not here. It is not here. It's in that little blue bar right here. Ideally, you want the score of that blue bar to be really high and the score of the gray bar to be really low. But in a regular transformer, it's not the case. And it uses something called signal to noise ratio. So here, the answer that we're actually looking for has a small signal compared to the overall noise that is included in this whole collection of contexts. So the issue is that the transformer tends to allocate a small proportion of the attention score to the correct answer. And the paper is trying to say that actually the real problem is not that it only allocated 0.03 to the blue bar, but also that these gray bar are not small enough. The difference between the blue and the gray should be bigger enough. And so in this work, the differential transformer, it employs a new architecture that is able to actually amplify the correct answer compared to all of the irrelevant context, which it also calls noise in this paper. That's a multi-needle retrieval. That's an important benchmark. This shows that the differential transformer is able to find the needle in the haystack much better than a regular transformer. Before we go into the architecture, the new architecture proposed by the differential transformer, let's just do a quick recap of what's a transformer, what is attention. So the transformer, really what it is, it's a learnable database. In a database you have query, it's maybe the indexes, you have the keys, so the properties of the data, and then you have the values, maybe it's the data itself. And all of these query key and values are learned on the fly. So the queries, you can think of it as, what am I looking for? It's looking for something. The keys, in a way, summarizes what the data represents. And then the values are the data themselves. So, for example, let's zoom in on an example of what attention really does. Here you have a sentence, he booked a room at a hotel. The purpose of attention is, for example, let's say I'm focusing on the word booked. I want to know how relevant is the word booked to every other token in the sentence. So the attention is actually going to search for how important is A to book, or is room to book, or is at to book, so on and so forth. After it does its computation, it's going to say that, okay, booked is actually 55% important to itself, and room is about 15% relevant to book, and hotel is about 30% relevant to book. Is going to add all of those different tokens weighted by those weights here, and it's going to come up with a new vector to the word booked based on how other words are meaningful to it. And so it's a more contextualized vector. So this is what attention does. If we take just a level deeper, how are we doing it? So what goes on here? How is it able to find those weights? That's what we're interested in. So the attention is actually how similar each one of those token is to this one. Okay, hence the equation right here. How does it do that? It takes the vector booked, which is a vector. Okay, it passes through 3 MLPs. So these are fully functional matrices, and it outputs, for the first one, the query. The second one outputs a key. The third one outputs a value. Okay. So the query, you can think of it as it's searching for something specific. The keys is summarizing from a certain aspect what the value represents, and then the value is the actual value we want to do. So here we're doing a dot product. So when you're dot product the query and the key, you're actually trying to, if the query, it's about what am I looking for, and the key, it's about what a value represent. So think of it as like the profile of my LinkedIn, let's just say. So it sort of summarizes the kind of work that I've worked on. So the query could be thought of as I'm looking for a profile that has the certain skill set. So when you're doing the dot product, you're actually trying to say, for the skill set that I'm searching for, how relevant is this profile? How of a good match is this profile based on the skill set that I'm looking for? So you can think of it as that. And then you have a score. The higher the score, the more there's a match between those two. And so this is another way of seeing it. So these are your tokens in yellow. You produce your keys, you produce your queries, and you produce your values. You are multiplying your queries and your values, and you're getting a bunch of unnormalized scores. You pass it through your softmax, and you're going to get a normalized attention scores. Okay. These are then multiplied by the value. You pass that through some kind of an output layer, and you get your new contextualized vector. One thing that I want to focus on is that the attention scores right here. So these attention scores is basically how we get these numbers right here. Okay, so it's important just to understand roughly what's the internal mechanism of the attention. So just to repeat what the problem is that the noise in these this whole collection of documents is actually distracting. It's distracting the transformer from attending to the answer right here. And what this paper is trying to do is trying to actually remove this noise. By removing this noise, the transformer will be less distracted, and it will be able to actually give a higher bar here, and it can also remove the noise on the side right here. The paper claims that when it applies the differential transformer, because it's able to better focus, it's able to cancel the noise, being less distracted by the noise, we can actually have less hallucinations, and we're better at retrieving information. We're better at modeling long context because we can better focus, and there's less hallucination, better in context learning, so on and so forth. So how does it cancel? So one thing I wanted to mention before is that this approach, it actually came from electrical engineering. There you go, it came from electrical engineering. for noise cancelling headphones and differential amplifiers, where the difference between two signals cancel out common mode noise. And that's important here, two signals. Okay, so how are we gonna use two signals in this, or this new, how do they use two signals in this architecture? If I go back here, so when you're creating a query and a key, you're actually creating a certain view of the data. When I create another set, so let's take, this is Q1, and this is K1, that's one set. Okay, you can think of this as a certain view of our data. If I create another set, Q2 and K2, I'm going to create a second view of the data. So both views have a certain angle on the data that we're looking at. So what's in a view? A view can be reinterpreted as sort of meaningful context plus some noise, some irrelevant context. Okay, the view 2 can also be interpreted the same thing, plus irrelevant context. But the difference between the two views is that the meaningful context in one and the meaningful context in two are going to be slightly varied because the sets are different. So you can think of this as like, this is meaningful context 1, this is meaningful context 2. So important signals will likely appear more strongly in one view than the other, and the noise statistically will appear to be sort of equal across the views. What happens if I subtract one from the other? Okay, if I subtract one from the other, then you're going to have your meaningful context 1 minus meaningful context 2, and the noise gets cancelled out. So what you're really left with is the difference between the two contexts. That's important because what we've just done here, we have removed, in a way, the noise, and we have come up with a new set of features, which is the difference between those two contexts. What's going on here is by subtracting one set from the other set, I've essentially canceled out the noise. So I've eliminated irrelevant context, and I've amplified meaningful context. And this is at the core of what's going on here. So here, when they say the difference between the two signals cancels out common mode noise, this is what they're doing actually. So here's your vector. You pass it through your query matrix. Instead of it outputting a D dimension query, we're actually going to output a 2D. And the same for the key. So basically this is going to be longer. Okay, the same with the key. It's going to be longer. So it's going to be 2 times longer. Okay, so I got this slide. I brought it next to this slide for better explanation. Okay, so basically what's going on here. So this is your X here. So this is what they refer to, the X here, or the X right here. So the X is going to go through a bunch of linear transformations to get your queries, keys, and the values. Okay, so for X, we're going to create 2 sets of query keys. So that's your Q1, K1, and then you have your Q2 and K2. And there's only one set of the V. Okay, just like here, we're dot product between the query and the key, and then we're passing it to the softmax, and we're actually getting our attention scores. We're going to have 2 attention scores. Okay, so here we're taking our x, we're multiplying by query matrix. Same thing with the key, we're splitting them, and this is how we're getting our two sets, right? The value is one set, so there's no splitting, you just have one. And then we're multiplying your q and your q1 and k1, and you're passing that through a softmax, and you have your first attention score matrix, you have your second one, which is equivalent to this one. So you're going to have two of those. Okay, you're going to have an A1 and A2. And the core mechanism in this differential transformer is that actually they're subtracting one to the other. And actually the second one is multiplied first by lambda, which is learned. Okay, so it's softmax of A1 minus lambda softmax of A2. And as I've explained, you're taking the difference in the perspectives. And by taking that difference, you're actually canceling out the noise. So there's going to be H heads. So each head is going to do the same work on a different chunk of the vector x. So let's say you have, let's say x is of 1024. This is the size of the vector, and you have 4 heads. So each head will focus on 256 dimension. And each one will be statistically different. So they're going to apply group normalization. So they're going to normalize each head, and then they're going to combine them. They're going to concatenate them, and then they pass through another output linear layer. And that's how you get your new X that's fed into the next transformer layer. It's important to note here that this makes a lot of sense from a downstream application perspective, because as you train this, the model is going to learn what constitutes noise versus the signal based on the performance of the downstream task. One last thing to mention is that as you're doing this, so as you're learning, the attention score for what you care about is going to be a lot. It's going to be high. The attention scores of the irrelevant context is going to be much lower. And what this will do is that's going to actually make your attention matrix, attention score matrix or attention map very sparse. The advantage of that is that now you open yourself up to algorithms that can make this compact, as they say here at the bottom. As the attention pattern becomes much sparser, we'd also like to utilize the property to compress key value caches. So not only is the transformer better able to focus and have better downstream performance, now you can compress it even more and make this run faster, cheaper.